training cutting-edge generative AI, especially these powerful diffusion models like Stable Diffusion, it's just notoriously expensive.
Oh, absolutely.
We're talking thousands upon thousands of A100 GPU hours just to get them ready.
It's immense.
And yeah, they're revolutionizing image and video synthesis, but that massive computational cost, well, it often limits who can actually push the boundaries here. It's a huge bottleneck.
And that bottleneck is exactly what this paper, TREAD, Token Routing for Efficient Architecture-agnostic Diffusion Training by Felix Krauss and the team at Comfis, is really trying to smash through.
Okay.
What's truly exciting, I think, is that this work doesn't just improve training efficiency, it also boosts the generative performance at the same time.
So it's like a double win.
Exactly. It's that rare, powerful double win that can, really change the game for researchers and developers.
Okay, so for anyone needing the quick version, the takeaway, TREAD introduces this novel training strategy for diffusion models. It dramatically cuts training costs and significantly boosts image quality. It does this using a clever token routing mechanism. You can kind of think of it like an express lane for data inside the neural network.
That's a good analogy.
Yeah, it sends specific data tokens from early layers directly to deeper layers. So it preserves crucial information, but cleverly skips unnecessary intermediate computations.
Right.
The result, you can get up to a staggering, 37x speed up in convergence compared to the standard diffusion transformer, or DIT.
37 times, yeah. That's impressive.
And you're reaching state-of-the-art image quality. Crucially, you don't need any architectural modifications or extra parameters in your existing models.
No changes needed there.
This really feels like a profound step towards, democratizing access to powerful generative AI R&D.
Absolutely. So for this deep dive, we're going to unpack precisely how TREAD achieves these really impressive results.
Okay.
We'll explore its unique approach to handling this information flow, dive into its surprising empirical findings, some of which really challenge common assumptions, actually.
Oh, interesting.
And then we'll discuss the practical implications for anyone, working with diffusion models today.
Okay, let's unpack this then. Why is training these models, especially something like the diffusion transformer, the DIT, such a computational beast?
Well, it really boils down to two core things: slow convergence and sample inefficiency. They're just incredibly hungry for data and processing power.
The numbers are. Yeah, they're frankly staggering. Training a single DIT on standard benchmarks, it can chew up thousands of A100 GPU hours just to get competitive.
And that's just for image benchmarks.
Right, and for text image models, it's even more extreme. Stable Diffusion, for instance, I think the figure was around 150,000 A100 GPU hours to train.
Something like that, yeah. It's astronomical.
When you hear figures like that, for most of us, it's like trying to picture the distance to the moon in grains of sand. It's completely unfathomable.
It really is.
It really puts into perspective why full-scale training remains this distant, almost impossible goal for so many research labs and, individuals.
It truly does. And, the AI community has poured a lot of effort into improving efficiency, but often it's focused on different stages.
Like fine-tuning.
Exactly. We have methods like LoRa, which is fantastic for parameter-efficient fine-tuning, or caching strategies that speed up inference, and various ways to personalize models.
Right.
These have made using the models much more accessible. But that initial full-scale training phase, still incredibly costly.
Yeah, that's the real hurdle.
And when we talk about training efficiency specifically, the existing methods, things like masking parts of the input or using distillation or making architectural changes, they often come with a trade-off.
Ah, okay. Like what?
Well, you might enhance performance, but at the expense of more compute cost. Or you reduce cost, but maybe hurt performance. It's often one or the other.
Right.
Which raises that important question, can we actually have our cake and eat it too? Can we get both better performance and lower training costs without compromising?
Okay, and this is where it gets really interesting, because TREAD seems to be saying, yes, you absolutely can.
Pretty much.
Its core innovation is this token routing. And you made a key distinction earlier. It's a training strategy, not an architectural modification.
Precisely. You don't need to fundamentally redesign your diffusion model or add new learnable parameters. It's like a smart software update for your training process.
Okay, I like that analogy. So how does it work?
Well, TREAD acts as this dynamic transport mechanism for randomly selected tokens within the network. Imagine information flowing through a factory.
Okay.
Instead of every single piece going through every single machine in sequence, TRED picks out a subset of components, these tokens, at an early stage, say layer lie, and then it gives them an express lane. These tokens bypass the intermediate machines, the computations, and they get reintroduced later at a deeper stage, LJ. They follow a defined route.
So they skip some steps?
They skip some steps, and this is really key compared to something like masking. Masking might permanently discard those components or replace them with a generic placeholder.
Which could mess things up a bit.
It can partially disrupt that incremental refinement process that's so core to how diffusion models learn. With TRED, the information loss is only temporary.
Whoa.
Those tokens still arrive at the later stage, fully intact, ready to be processed by the more refined parts of the network.
So it's not throwing information away, just giving some of it a smart shortcut.
Exactly, a shortcut.
And it seems to fit really seamlessly into the established diffusion framework. You mentioned it uses the standard continuous time diffusion process, like the Keras EDM formulation.
Yep, it sticks to that. And it uses a single reconstruction loss across all tokens.
Which keeps things simple. No complex loss balancing acts.
Exactly, keeps it clean. The tokens chosen for routing are randomly selected for each training sample, typically at a fixed rate, maybe 50%.
Okay, and how are they selected? Is it just random?
For transformer models like DIT, yeah, it's a simple random selection of tokens. For other architectures, like the sequential RWKV model, they found row selection worked a bit better. And here's maybe the most practically appealing part. This routing. It only happens during training.
Oh, only during training.
Only during training. For inference, when you actually use the model to generate images, the standard full network pathway is used.
So there's zero overhead at inference time.
Absolutely none. Your trained model runs just as fast as a conventionally trained one. You just got there much, much cheaper and potentially with better quality.
Okay, so what does this actually mean for overall performance then? TRED somehow manages this amazing trick of boosting both training efficiency and training effectiveness. How does it pull off that dual benefit?
It's this really neat multiplicative advantage. So on the efficiency side, it's pretty straightforward. By skipping layers for a chunk of tokens,
You save compute.
You get linear reductions in the feed-forward networks, the FFNs, but even more importantly, you see quadratic gains for the self-attention layers.
Quadratic. Why quadratic there?
Because self-attention complexity scales quadratically with the number of tokens being processed together. Fewer tokens interacting means a much bigger saving.
Got it.
So even small routing rates give you noticeable cost reductions, and the savings really ramp up with the route length, how many layers you skip.
Okay, that covers the efficiency boost.
Yeah.
But what about the effectiveness? You said it actually improves the final model quality too.
Yes, and this is the really fascinating, slightly counterintuitive part. Normally, diffusion models process all tokens through all layers. TRED introduces variance, right?
Because some tokens skip layers.
Exactly. The network has to learn the denoising step with a variable number of layers processing the information. And what's really intriguing is that longer routes, which introduce more variation and actually lead to a higher training loss compared to the baseline, especially early on.
Wait, hang on. Higher training loss leads to better final performance. That sounds, well, wrong. My brain wants lower loss for better performance.
Yeah, it does sound counterintuitive, right? But think of it like this. You're adding a kind of beneficial challenge or noise during training.
Okay. Like making it work harder.
Sort of. When the network is forced to reconstruct images, even when some information took a shortcut, it has to develop a more robust fundamental understanding of the data. It can't just rely on perfectly refined info from every layer.
So it forces better generalization.
That seems to be the effect. It has to learn more resilient representations. So that initial higher difference in training loss compared to the baseline isn't a bad sign. It actually indicates the routing mechanism is having a strong beneficial impact, pushing the model to be more robust.
Wow, okay. That's a cool insight.
So you're not just getting more iterations per second because it's cheaper.
Each iteration is actually more effective too.
Exactly. It's a multiplicative speedup. More iterations per second times more effectiveness per iteration. That's where those big numbers like 37x come from.
The numbers are pretty compelling, aren't they? This isn't just theory. The paper has solid empirical results.
They really are solid. On the standard ImageNet 256 benchmark, TRED hits a, 14x convergence speedup at 400K training iteration.
Oh, he's already great.
And then a massive 37x speedup by 7M iterations compared to the baseline DIT.
Yeah.
And the quality is there too. It reaches a competitive FID.
That's the Fréchet inception distance. Lower is better quality.
Right, lower is better. It gets 2.09 FID in a guided setting, 3.93 unguided. That's a direct improvement on DIT with 0 architectural changes.
And compared to other methods.
It outperforms state-of-the-art approaches like MDT and SDDIT in effectiveness and things like mass-DIT inefficiency. The iteration rates are way up, 3.03 iterations per second versus DIT's 1.86 or MDT's 1.02 on the same hardware.
So faster iterations and better results per iteration.
Exactly. If you look at the graphs in the paper, like figure 1 and 5, it's visually clear. TRED needs way less GPU time to hit a much lower FID.
And the actual images.
Oh yeah, the qualitative samples look fantastic. Orcas, golden retrievers, elephants, forklifts, post boxes, really diverse stuff showing improved fidelity.
And a key point you mentioned earlier, it's not just for DIT models, it's architecturally agnostic.
That's a major strength, yes. TRED's effectiveness carries over seamlessly to other token-based sequential models. They tested it on Diffusion RWKV.
Which is a state space model, quite different from a transformer.
Right, and it consistently improved performance there too, across various model sizes from small up to XL. This broad applicability is huge.
That makes it much more generally useful.
Definitely. And what's also fascinating is its modularity. You can combine TRED with other unrelated improvements.
Like stacking optimizations.
Pretty much. They integrated it with RePA, which is a representation distillation technique, and got even better generative performance.
So TRED can be like a foundational boost that other methods can build on top of.
Exactly. It enables compounding gains.
Does it scale well? What about higher resolutions or different tasks?
Seems so. They validated it at ImageNet 512 resolution and even on text-to-image with MS-OCO.
Which is much tougher.
Much tougher. And even there, TRED showed substantial FID reduction and significantly faster training speeds. Seems quite robust.
Okay, this is all sounding great, but for people listening who might want to actually use this, one of the most valuable bits is often the practical guidance. The authors did ablation studies, right, to figure out the best way to set this up.
They did, and this raises that key question. How exactly do you design these routes for the best results? The ablations offer surprisingly clear answers.
Okay, lay it on us. What do they find?
Well, first, route location. Generally, longer routes lead to better performance.
Longer meaning skipping more layers.
Exactly, skipping more intermediate layers. The optimal starting layers are usually very early in the network, like up to layer I2.
So right near the beginning.
Right near the beginning. And the optimal ending layers are relatively late, say up to J8 in their 12-layer tests. But there's a catch.
Yo.
Choosing an excessively late end layer, like J10 in that 12-layer model, can actually hurt performance.
Why is that?
The thinking is the network still needs enough capacity, enough layers after the routed tokens rejoin to properly integrate them back into the flow and make sense of them.
Okay, so you need some processing room at the end.
Precisely. And remember that counterintuitive loss thing?
Yeah, the higher early loss difference correlating with better results.
The studies reinforce that. A higher difference in early training loss compared to the baseline seems to be a good indicator that the routing is having a strong positive impact. It's a useful signal to monitor.
Interesting. Okay, what about how many tokens to route? The selection rate?
Right, the selection rate. The sweet spot seems to be around 50% random token selection.
Half the tokens take the express lane.
Roughly, yeah. A lower rate, like 25%, still works pretty well. Better than the baseline DIT. But if you push it too high, say 75%,
performance drops.
Performance actually degrades. It ends up worse than the vanilla DIT baseline.
Even though it's technically more efficient to train.
Right. The theory is that if too many tokens skip the main path, the model just doesn't get enough information processed through the full network depth to learn effectively. So 50% seems like a good balance between efficiency gains and effective learning.
Makes sense. Anything else from the practical side? What about bigger models?
Yes, crucial point about scaling. When you go to larger models with more layers, how do you adjust the route?
Do you scale the layer indices proportionally?
Intuitively, you might think so, but no. They found the optimal route location scales in an absolute manner.
Absolutely. How so?
Meaning if I2 and J8 were optimal for a smaller, say 12-layer model, you should aim for I2 and JB4 for a larger model with B total layers.
So you keep the start point, I2 fixed near the beginning, and the end point, a fixed number of layers from the end of the network.
Exactly. You don't scale J proportionally like J over 12B. You keep it B4. That's a really critical, practical guideline for researchers applying this to bigger models.
That is super useful. Okay, so we've really dug into TREAD here. It feels like a genuinely impactful paper tackling one of the huge pain points in generative AI.
It really is.
It's not often you see something that manages to cut costs and boost performance simultaneously, especially without adding complexity or new parameters to the model itself.
That's the rare combo, yeah. It's incredibly significant because it really could make these powerful diffusion models accessible to a much wider range of people.
Democratizing the training process.
Exactly. Democratizing the ability to train these complex systems. That could potentially accelerate innovation across the board. Visual synthesis, 3D generation, who knows what else.
So, thinking about the folks listening, what does this mean for you? If training diffusion models felt out of reach because of the sheer compute cost, well, TREAD offers a proven, highly effective path towards both efficiency and higher quality results.
Right.
Imagine the new possibilities if these state-of-the-art models become dramatically cheaper to iterate on, to experiment with, to deploy. What new applications or research directions might you explore then?
It really pushes us to think critically, doesn't it? About resource allocation, about what becomes feasible when that compute barrier is significantly lowered.
Yeah.
How might this shift impact the speed of progress in fields like visual synthesis, or maybe even areas like drug discovery or material science where these generative models are starting to make inroads? It opens up a lot of avenues.
Definitely food for thought. If you want to try it out, the code for TREAD is available on GitHub. The path is https://github.com/uppompieverred.
And definitely check out the full paper. There are more details, figures, and ablation results in there.
For sure. Well, thank you for joining us on this deep dive into TREAD, token routing for efficient architecture-agnostic diffusion training.
My pleasure.
We really hope this discussion has given you some valuable insights and maybe sparked some new ideas for your own work. Until next time, keep exploring.